Hey there, welcome back to another episode in the PTX series. In the previous videos, we explored the PTX NFC SDK from Renesas and walked through a quick demo using the example project. But in real-world applications, you'll often need to integrate NFC functionality into your own project. In this episode, we will take a look at how to approach that integration step by step. First, we need to find a compatible Renesas board to host our project and connect to the PTX hardware module. In this demo, we'll be using the EK RA8D1 board and PTX105R PMOD for Quick Connect module. The project we'll be using is a Hello World example for the RA8D1. We will be integrating NFC into this project. You can find more details in the application note. Just head over to the website and under the Design and Development section, look for the GUI Hello World project with a MIPI LCD display. The first step in our workflow is to import the project. To do that, we will start by opening eSquared Studio, just like we usually do. Next, we will import the project by selecting the zip file we just downloaded. Once the project loads, you will see that it already includes source files for the display module. There's a Seger library, a touch library, and individual source files for each thread. If we navigate to the Stacks tab, we can also see several configured stacks, including the Azure RTOS, which is already integrated into this project. A quick look reveals that this project is already using an external interrupt, an I2C channel, and a timer. The next step is to set up a new thread that will run the NFC application. Now, before we go ahead and create the NFC thread, we're going to import a standalone NFC example project. This will serve as a reference in case we need to match any configurations. Once the project is imported, you will notice it includes some source files that we will need to use in our own setup. Let's go ahead and configure the actual NFC thread. To start, we'll open the configuration file from the base NFC project to see what's already set up there. In the configuration file, we will see an interrupt, a timer, an SPI channel, and a UART stack being used in the base NFC project. Next, we will switch to the FSP configuration view to take a closer look at these individual stacks. Next, we will create a new thread in our existing project. The first thing we'll do is rename the thread to PTX thread. Then, we'll update the symbol to match PTX thread. First thing, we need to increase the stack size to 4K. Now, let's take a look at the stacks required for the NFC. We will need an external interrupt, a timer, an SPI, and a UART stack, though the UART stack is only for debug messages. Now let's configure the interrupt request. We will name it G_X_IRQ, set it to channel 1, and use the callback PTX GPIO ISR callback. For the pin, we'll select pin 508, which corresponds to IRQ1 on this board. Next, let's add the stack. We'll rename it, set the channel to 1, and configure the trigger to rising. The callback function will be PTX GPIO ISR callback. Finally, we will set the priority to 3. You will notice that no pin has been assigned to this interrupt yet. To assign it, click the small arrow, which will take us to the configuration page for this pin. Here, we will set IRQ1 to pin 508 since that's the physical connection between the PMOD port and the MCU. If we navigate to the P508 configuration, we will see that the pin is now assigned as an interrupt and its name is set to PMOD2. This completes the configuration for the interrupt pin. Next, let's configure the timer module. We will create a new timer, which will be a general purpose PWM timer, and name it R_GPT. The name G_timer0 is fine, so we will keep that. Next, we will set the period to 10 milliseconds. Make sure to enable the callback function. This is a crucial step as the timer needs a precise callback to function correctly. We will follow the usual naming convention for this project and name the callback PTX_timer_ISR callback. Additionally, we will set the overflow interrupt priority to 3. Next, we will configure the SPI channel. To do this, we first need to review the layout of the PMOD port. As you can see, male port is from the PMOD module, and on the RA board, it's a female connector. This PMOD2 port will be used for the PTX module, and the SPI channel we will configure is channel 2, which uses IRQ1. The chip select pin PF5 needs to be set as GPIO output. Lastly, make sure that these pins are not being used by any other module in the project. So we will add a new connectivity stack from the SCI-B channel. First, we will set the channel number to channel 2. Most of the settings can remain at their default values, but we will go ahead and change the name of the callback function. Following the previous naming convention, we will name the callback PTX SPI transfer callback. The bit rate will be set to 1 million bits per second. Next, we will notice that the pins have already been assigned since we selected channel 2. One important thing to note is that the chip select pin must be disabled in the stack properties. Instead, we will go and change the actual pin configuration to output mode, as this pin will be controlled by the software as a GPIO pin. Finally, we'll change the name of the stack to match the references used within the SDK source files. Next, we'll configure the UART channel, which will be used for debugging and exchanging log messages. For the connectivity, we will again choose an SCI-B channel, which is used for UART. Let's start by changing the name of the channel. For this board, we will use channel 9. The baud rate needs to be set to 115/200, and luckily it's already configured correctly. Next, we will change the name of the interrupt callback. Since this is a 2-pin exchange, we will ensure the pins are correctly assigned, and it looks like they are. We notice that the stack name is highlighted in red, so let's hover over the I button to check what the issue could be. It appears that we need to enable the specific clocks required by the SCI channel. Let's navigate to the clocks tab and locate the clock named SCI CLK. It's currently disabled, so we will enable it with the PLL1 source. Then we will set the clock frequency to 60 MHz, by selecting the appropriate dividing factor. Once we make these changes, the red highlight will disappear. With the stacks now set up, we can go ahead and click on Generate Contents to create the library files for the NFC API based on our stack configuration. Next, we will add the source files for the NFC application into our project. For this demo, we will take the files from the default standalone NFC application and paste them into the source folder of our existing Hello World project. Now that the files are added, we need to remember that in our previous project, we likely had a custom build configuration that excluded some files we didn't need for this operation. By pasting these files into our existing project, all of them are now active and part of the build. To resolve this, we will go through the files individually and exclude the files we don't need for this demo. We will start by excluding the files associated with the I2C and UART communications between the board and the PTX, as our module uses the SPI protocol exclusively. We will also exclude the AppTimer files, as well as the platform-specific I2C and UART files. And we will also exclude the folder for the IoT App Test API. Next, we will verify that the pin configuration in the source files are correctly hard-coded. We will start by checking that the IRQ pin is properly set in the GPIO file. Then, we will review the SPI channel number and the chip select pin assignment to ensure they match our setup. We will review how the HAL entry file is set up in the barebone project, since we need to apply similar logic in the PTX thread of our Hello World application. An external reference is made to the PTX app entry function, so we will do the same within our thread. We will also include the HAL data file to ensure proper access to hardware definitions. In this part, we will add the necessary preprocessor definitions to the project. The complete list of preprocessors can be found in the provided text file. Once all the definitions have been added, we will apply the changes and close the Properties tab. The next step is critical. We need to carefully add all the directory paths that may contain header files associated with the PTX stack. It is important to ensure that no required folder is missed to avoid build errors later on. In this section, we'll replace the old blocking wait sequence in the IoT Reader SDK with a proper semaphore-driven design. This allows the IoT Reader thread to sleep until an event happens instead of locking the CPU. First, we create a binary semaphore with an initial count of 0. This acts like a signal line between interrupts and the IoT Reader thread. The thread will wait on it, and the interrupts will release it. Next, in main.c, we also declare our threadx semaphore variable and initialize it during startup. This ensures the semaphore is properly set up before the IoT Reader thread begins waiting on it. By placing the declaration and initialization here, the semaphore becomes available globally to the platform functions that will signal it from interrupts. After setting up the semaphore, we need to update 4 functions in the platform code. In PTXplat.c, we'll modify PTXplat wait for interrupt. In PTXplat timer.c, we'll update both PTXplat timer start and PTXplat timer ISR callback. And in the PTXplat GPIO.c, we will change PTXplat GPIO ISR callback. These updates remove the old blocking behavior and make each function use the semaphore to signal the IoT reader thread only when an event occurs. In the original non-OS SDK, the wait for interrupt function just spun in a tight loop until an interrupt occurred, blocking the CPU. In our Azure ThreadX RTOS version, inside PTXplat.c, we replace that waiting mechanism with TX semaphore get. For other RTOS, such as FreeRTOS, you need to use a similar code suitable for that platform. Now the IoT reader thread simply waits on the semaphore and sleeps until it's released by an interrupt. This keeps the CPU free to run other threads. The timer start function in PTXplat timer.c blocked the CPU in certain modes until the timer expired. We replace that blocking logic with a semaphore wait. The thread calls TX semaphore get, and when the timer expires, the ISR puts the semaphore to wake the thread. In non-blocking mode, the behavior remains the same. The GPIO interrupt callback in PTXplat GPIO runs whenever the NFC device asserts its IRQ pin. In the non-OS SDK, hardware woke the CPU directly, so no action was needed. In RTOS, we explicitly release the thread by calling TX semaphore put. This wakes the IoT reader thread right away to handle the external event. The timer interrupt callback in PTXplat timer works the same way. When the timer expires, the callback calls TX semaphore put, releasing the semaphore and waking the IoT reader thread. This ensures accurate timing without blocking the CPU. With these updates, the IoT reader thread only runs when there's real work to do. The blocking states are now handled cleanly through semaphores, making the design scheduler-friendly and efficient. We have already talked about how the application layer does not depend on any one platform. That's why we have a platform layer. It steps in as the middleman, connecting the hardware to the application so everything works smoothly across different systems. The platform-specific files are managed through the PTXplat file. This file, in turn, relies on 2 others, int and ext. All API functions of the plat component use a component-specific data structure called PTXplat_t. This structure is defined in PTXplat int.h. Finally, PTXplat_ext.h contains include directives and compiler-specific disabling of warnings for third-party code. This code lies outside the scope of the SDK provided by Renesas. Now, our project is an RTOS project. We configured the FSP drivers for the PTX in a single thread, so only including HAL data is no longer sufficient. The FSP configured stacks are now available through PTX thread. So, for correct referencing and to resolve any compilation issues, we will update the PTXplat_ext.h file to include the PTXthread.h. Once these steps are done, we are ready to build. We can see that the project builds without any errors. Those were the essential steps for embedding the NFC components into your project. Depending on your project specifications, you are expected to make sure all required files are correctly placed within the project directory. As long as the source files can find the right header file, you can organize your project to your convenience. And that's it for this part of the tutorial. See you in the next video.